Understanding the centroid of volumes is a fascinating journey into the heart of geometry and physics. When we talk about the centroid, we're essentially referring to the center of mass of a three-dimensional object. Imagine balancing a solid object on the tip of your finger. The point where it perfectly balances is its centroid. To find the centroid of a volume, we often use a method called integration. This might sound complex, but let's break it down. For a solid with a uniform density, the centroid can be found using the formula that involves the coordinates of the volume. Specifically, if we have a solid defined by a function in three-dimensional space, the coordinates of a centroid, x, y, z, can be calculated using these integrals. Here, v represents the total volume of the solid, and dv is the differential volume element. This means we're summing up all the tiny pieces of volume, each weighted by its distance from the origin, and then dividing by the total volume. Let's consider a practical example: finding the centroid of a solid hemisphere. The hemisphere can be described in spherical coordinates, which makes our calculations a bit easier. The volume element in spherical coordinates is given by dv equals r superscript 2 sin phi dr d phi d theta. By integrating over the appropriate limits for r, phi, and theta, we can find the centroid's coordinates. For a solid hemisphere of radius r, the centroid along the z-axis turns out to be at a height of 3 r/8 from the base. This result is not just a number. It tells us where the mass of the hemisphere is concentrated. Now, what if we have a composite solid made up of different shapes? In this case, we can find the centroid of each individual shape and then use the concept of weighted averages to find the overall centroid. This is particularly useful in engineering and architecture, where structures are often composed of various materials and shapes. Another interesting aspect of centroids is their application in real-world scenarios. Engineers use centroids to ensure stability in structures, while designers consider them for aesthetics and balance in products. Understanding where the centroid lies can help in predicting how an object will behave under different forces, which is crucial in fields like robotics and aerospace. In summary, the centroid of volumes is a key concept that connects geometry with practical applications. By mastering the calculations and understanding the principles behind them, you can gain insights into the physical world around you. Whether you're designing a new product or analyzing a structure, knowing how to find the centroid can make all the difference. The centroid of a volume is like the balance point of a solid object, where all its mass is evenly distributed. Imagine a 3D shape, like a cube or a sphere. To find its centroid, we use the principles of geometry and calculus. For simple shapes, the centroid is often at the geometric center. But for irregular shapes, we break them down into smaller, manageable parts. Why does this matter? Knowing the centroid is crucial in engineering to ensure stability and balance in structures like bridges, buildings, and vehicles. It's also fundamental in analyzing forces, moments, and stress distribution. Let's take a cone as an example. Its centroid lies along its axis of symmetry, and for a uniform cone, it's located at a height of 1/4 the total height from the base. Similarly, for a sphere, the centroid is right at its geometric center. The centroid can be calculated using integrals, considering the density and dimensions of the volume. It's fascinating how this concept applies in engineering and physics, helping us design stable structures and understand the behavior of objects in motion. In essence, the centroid not only defines balance, but also plays a crucial role in determining how forces act on an object. Understanding these principles opens up a world of possibilities in design and innovation. The concept of the center of volumes is fascinating and plays a crucial role in our daily lives. It is also known as the center of mass for a homogeneous object, plays a critical role in many real-life applications across various fields. In engineering and construction, the centroid is essential for designing stable structures such as bridges, buildings, and water tanks by ensuring weight is evenly distributed. It also aids in the design of cranes, where balancing heavy loads is crucial. In transportation, the centroid determines the stability of vehicles, ships, and aircraft. For example, aircraft require precise centroid calculations to maintain balance during flight, while ships rely on a centroid and buoyancy to remain stable in water. Similarly, in car design, the centroid affects handling, performance, and resistance to rollover. Imagine designing a bridge. Engineers must calculate the center of mass to ensure stability and safety. If the weight distribution is off, the structure could collapse. In architecture, the center of volumes helps create aesthetically pleasing buildings that are also structurally sound. Think about sculptures. Artists consider the center of mass to ensure their creations stand firm without tipping over. Even in sports, like gymnastics, athletes use their understanding of balance and volume to execute flawless routines. This principle is everywhere, from the cars we drive to the furniture we use, influencing design and functionality in ways we often overlook. Understanding the center of volumes not only enhances safety, but also sparks creativity in various fields.
So may example naman tayo guys. Yung problem is locate the centroid of y para y bar of the paraboloid. So bali yung formula natin na y bar is equals to integration of y tilde dv all over integration of dv. Tapos z bar is equals to z tilde dv all over integration of dv. Makikita natin guys na nasa gitna naman na yung itong natin, paraboloid. Same na 4 meters na yan. Kaya bali yung center na nung sa may z part natin is z bar is equals to 0 na. Ayan. Para ma-solve natin to guys is nagawa tayo ng cylinder dito na maliit. Ayan. Bali yan yung center. And radius. Then yung height. Bali yung volume ng cylinder natin is equals to bali yung volume ng cylinder natin guys is pi r squared tas yung height. Pero yan natin yan as dv naman. Bali dv is equals to pi, bali yung r magiging z squared, and then itong height nya is magiging dy na. Dy dy. Yan. So ipa-plug lang natin to sa may natin formula para ma-solve na yung natin centroid ng y bar. So bali pa-plug na lang natin y bar is equals to integration of bali yung may pa pala to, yung upper and lower limit. So bali 0 to 4 y, bali yung dv kanina pi for y kasi makikita naman natin na yung value ng z squared is 4y. So that's dy. Ayan, tapos dito same ulit, lower limit 0 to 4, tapos dv pi yung z squared 4y dy. Ayan. So pwede natin siya tong i-direct calcu, pero pwede rin muna tayong simplify pa lang muna natin to. Simplify muna natin yan. Pwede pa ma-simplify ito, bali maging equals integration, bali pwede yan maging 4y pi or pi y squared dy all over integration of 0 to 4 pi for y dy. Yan. So bali ang magiging sagot na dito is 4 pi y cube all over 3 from 0 to 4. 0 to 4, tapos yung sa may naman denominator is magiging naman na siya 2 pi y squared. Same din na from 0 to 4. Bali ang sagot na dito guys ay 8 over 3. Or approximately 2.67 in terms of meters. Good day. We are working on centroid with composite shapes. So this one is going to deal with volumes. So our goal is to find the centroid of the given items: x bar, y bar, and z bar. For our step 1, we are going to break this into shapes. So this is shape 1, this will be shape 2, this is shape 3, and this is shape 4. Next step, we will use the table method of Jefferson. Here we got x bar, y bar, z bar, volume, xv, yv, and zv. And that's the tabletop parts. And then the bottom part is 1, 2, 3, and 4. X bar is equal to the summation of xv over summation of v. Y bar is equal to summation of yv over summation of v. And z bar is summation of gv over summation of v. Piece number 1, follow yung x direction, which is makakita ka ng right triangle. So it's going to be at 1/3 the base, which is 1. So 3 plus 6 plus 1 is equal to 10. Yung sa y direction of shape number 1, kalahati ng thickness, which will be 1.5. As for the z direction, yung height niya ay 8. So yung z bar is located at 1/3 the height, which is 8/3. Para sa x bar ng shape number 2, kailangan i-add yung 6 at additional 3 inches, then divide by 2, which is 4.5. As sa y bar, ay same process sa y bar ng shape number 1, which is 1.5. Sa shape number 2, makikita yung z bar sa gitna ng rectangle. So that is 8 divided by 2, which is 4. Now, the x bar of shape number 3 is half of the thickness, which is 1.5. As for the y bar, 8 divided by 2, which is 4, plus the additional 3 inches is equal to 7. And z bar is half of the height of the rectangle, which is 4. Sa x bar, same process sa x bar ng shape number 3, which is the half of the thickness, which is 1.5. Sa y bar, additional 3 inches plus 8 plus 1 from the right triangle, which is 12. And the z bar of the shape number 4 is at 1/3 the height, which is 8/3. The volume for a triangular prism is the area of a side times the thickness. So 1/2 base times height. So 3 times 8 is equal to 24. Divided by 2 is equal to 12. 12 times 3 is equal to 36. Same lang din sa shape number 4. So it is also 36. So sa shape number 2, that is 9 inches long. So 9 by 8 is 72 times 3 wide is equal to 216. And rectangular prism of shape number 3 is 8 by 8, which is 64. 64 times 3 is equal to 192. Sa pagkuha ng xv ay x times v, which is 10 times 36 is equal to 360. For yv, 1.5 times 36 is equal to 54. For gv, 8/3 times 36 is equal to 96. And same process sa 2, 3, at 4. For the next step, kailangang i-compute yung summation ng v, xv, yv, at zv. At the summation of v is 480. The summation of xv is 1674. the summation of YV is 2154. And the summation of ZV is 1824. X bar is equal to 1674 over 480. Y bar is equal to 2154 over 480. Z bar is equal to 1824 over 480. X bar is equal to 3.4875 inches. Y bar is equal to 4.4875 inches. And Z bar is equal to 3.8. So this is the location of the centroid.
We are here to explain how the antennas work in centroid and volume. So as you can see, we have our antenna here, and today we will explore the basics of the antenna technology focusing on the centroids and volume. So imagine na itong antenna na ito is napapalibutan ng electromagnetic waves and radiation which is nagtatransmit ng signal sa ating mga TV. To pinpoint where the centroid is nandito siya, which is also the center of the antenna. So bakit pareho ang center ng antenna at saka ang centroid ng electromagnetic waves and radiation? Kasi di ba sinabi ko kanina is napapalibutan siya ng electromagnetic waves and radiation which is symmetrical.
So how the centroid affects the antenna efficiency? The centroid have a huge role on the antenna efficiency due to change of the composition or distribution of the current in the antenna. So itong centroid, nakaka-affect din siya dun sa distribution ng current dito sa mismong antenna, which is nakaka-affect din siya dun sa nakaka-affect din siya dun sa pag-receive ng signals ng antenna. In the other hand, centroid optimization improves the antenna gain of signals that help us to enjoy program on the television. While the location of the centroid have impacts on directivity or connectivity. So itong centroid, nakaka-affect din siya doon sa direct connectivity which is yung parang pag-receive ng signals para ma-process, para may mapanood tayo sa ating mga television. And also, the centroid optimization improve the signal to noise ratio. So what is signal to noise ratio, or SNR? It's a measurement that compares the strength of a signal to the strength of the background noise. It is used in science and engineering to evaluate the quality of the signal.